space.
And I'm Hannah Critchlow. I'm a neuroscientist obsessed with all things brainy. So this is part of a new and interactive BBC science show called Tomorrow's World. And with your help, we're going to be exploring how science and technology is changing the way that we lead our lives and how it's also going to be shaping future humanity.
Over the last few months, we've been at the Science Museum in London, talking about whether humans will reach Mars in our lifetimes, and the Museum of Science and Industry in Manchester, exploring how we'll adapt to living with robots in the future. You can still catch those shows online on the BBC Tomorrow's World Facebook page and on the BBC's YouTube channel.
But for the next 40 minutes tonight, we're going to be exploring the organ that makes all of these things, robots and space travel, even possible, the human brain. That's right, Jen, it's payback time. So you may have taken me to outer space in previous episodes, but tonight, buckle up, because sister, we're going to go on a journey to inner space.
Fine.
Oh yes, so we're going to be exploring this 1.5 kilogram of grey fatty tissue mass that sits on the top of everybody's head. And it magically creates our sense of reality. It shapes our emotions and our decisions and how we interact with the world.
We're getting straight in there with the big topics. Hannah's just like,
Whoa.
straight in there. What I want to know, though, is what are the cutting-edge technologies that are changing the way we treat the brain when it's ill and look after it when it's well?
And in what ways are we going to be able to enhance our brains in the future? Well, luckily, we're going to be joined by some fantastically brainy experts who are currently waiting in the wings.
Oh, Hannah, don't get ahead of yourself. Get it?
Ahead?
Oh, yeah. Anyone? Never mind. Thank you. This show is all about you, the audience. If you're watching live online, you can post your questions in the comments on Facebook and YouTube, or you can get in touch on social media using the hashtag #MyTomorrow.
And we've had some excellent questions already in from audience members. For example, things like, what happens in your brain as you learn? Or could we one day download new skills directly into our brain so that we could, for example, start to kung fu fight, Matrix style? Or maybe I could be able to speak Mandarin like that.
Yeah, please do keep your questions coming in. But first, a huge welcome to our audience live here in the flesh at the Glasgow Science Centre.
Woo!
So, Hannah.
Yes.
The brain.
Yeah.
It's been called the most complex machine in the entire universe.
Yeah, and in order to try and understand exactly how it works, let's take a look under the hood and welcome our first guest for the evening, Yolanda Ahini from University College London. A warm welcome. Woo!
Yolanda, you spend all of your time looking at really detailed images of the brain, right? And I think you're working on a new type of MRI. Could you tell us a little bit more about that?
Yeah, sure. So I'm a PhD student at the Centre for Advanced Biomedical Imaging, and so I'm developing a new way of looking at the brain, and specifically how fluid moves around the brain and into the brain tissue. So I'm actually a physicist, and so I spend my time taking very detailed images of the brain and then use computational modeling to extract new dynamic information from these images.
I'm going to high-five you for being a physicist.
Yeah, well, I feel like I'm being ganged up on here. There's a show about the brain, it doesn't seem fair. But there's been kind of really a revolution in technologies that are allowing us to peer into the brain as never before with much higher resolution so that we can start seeing things in much greater, finer detail. That's right, isn't it?
Yeah, that's right. And specifically, a lab called Kubrick in Cardiff has produced this really nice image, really very high detail of the brain. And it's a very unique MRI scanner, and there's only 3 in the world, and one of them's in the UK. And so they've been working in collaboration with Siemens to take these really high detailed images of the brain, and so you can see actually those axonal connections in the brain.
Oh, right. So these are from the Cardiff University Brain Research Imaging Centre, but I want to take a step back because I've got to admit I'm getting a little bit lost about what all this means. So Hannah, you're a neuroscientist. Can you take us back to basics and give us a super quick guided tour of the brain?
Okay, I'm going to try to. So in your brain, Jen, there is about 85 billion nerve cells. So each one of these nerve cells looks a little bit, there should be an image coming on screen right about now. or maybe a little bit later. So that's it, there we go. Inside your brain, there's about 85 billion of these guys, so that's about 14.5 times the number of people on this planet in terms of nerve cells in your head, which is a whoppingly large number. And each one of these cells has a cell body, that kind of blob structure, and then extending out is that axon, that long cylindrical structure. And basically what happens is that signals come in from the outside world, get interpreted by your senses, and then your nervous system transduces those signals from the outside world into electricity that zips along that long cylindrical structure of the axon. So a thought is kind of a fizz of electricity in your mind. Now, magically, each one of those nerve cells in your brain connects to about 10,000 other nerve cells, making the most complicated circuit board ever imaginable, with about 100 trillion connections in the mind. So, your brain, Jen, is in essence, taking a very reductionist approach here, a circuit board.
I'm really pleased she's managed to put it in physics terms, electricity and circuit boards. So these are things that I can actually understand. That's great. If we now go back to the Kubrick's high-resolution MRI images, Yolanda, can you talk us through a little bit more what we're actually seeing here?
Yeah, sure. So the MRI image is sensitized just to the axonal connections, as Hannah was describing. And so the idea is if we can build up a picture of what the normal brain looks like, then perhaps if the brain malfunctions a little bit, then we'll be able to detect these changes. And what the director of Kubrick told me was that getting these MRI images is like having the Hubble Space Telescope when you've just been using binoculars before.
It's a nice space analogy. They're really talking in my language today. This is great. These images are genuinely awesome. I know we use that word a lot, but this genuinely is awesome. Yolanda, you're going to go backstage now and join in the conversation on the BBC Tomorrow's World Facebook page, but thank you very much for joining us here on stage.
Jen, I am really excited. As a neuroscientist, I feel as though we're on the cusp of some really exciting discoveries about how our brains form our thoughts and emotions and everything, how it does, all of the things that it does. We're kind of at the next frontier of humankind of discovery. I think, Jen, we are living in the era of the brain. Oh, yes. How does it make you feel?
I mean, I'm not going to lie. I get a little bit freaked out when I think about all this stuff going on inside my head, and then I'm like, it's my brain thinking about how weird the brain is, and then, yeah, it all gets a bit much sometimes.
And this electricity is forming you, making you think about how bizarre it is. It's so bizarre. It's so mind-boggling. But please be reassured, Jen, that I think that neuroscience knowledge is actually empowering. Don't be scared.
Yeah.
So, there's billions of nerve cells in your brain and trillions of connections. And we can possibly reduce how our brain operates and how it gives rise to us and how it makes us so unique down to this circuit board of activity. But is that too much of a reductionist approach? Is there actually more to us than just this circuit board of activity? Well, to try and explore this age-old question, let's invite our next guest onto the stage. So please give a warm welcome to Professor Helen Minnis, a psychiatrist from the University of Glasgow. Hey, Helen. And we're also welcome to have on board Britt Ray, who is the Tomorrow's World podcast presenter and science writer. Hello, Britt.
Right, let's get straight into it. Helen, you're a psychiatrist, and your focus is, as I understand it, less on kind of the functioning of the brain as an organ and more on the individual around it, the mind.
Yes.
Yeah. So is it important to distinguish between the brain and the mind? What is the difference between the two? Are they essentially the same thing?
You know, it's something I haven't given a lot of thought to because to me it's not massively important, but I think the brain is the main organ of the mind. But it's not the only organ of the mind because the brain and the body are totally interconnected. So.
And there's some really fascinating research that's coming out at the moment, isn't there, about how the immune system, how different activity in the immune system affects the brain.
Absolutely. So what I find fascinating is that our stress response systems and our immune system and our brain are intimately connected and they all kind of work together.
Mm-hmm. And even the gut, so the gut-brain axis, there's some fascinating research coming out there about how microbes in the gut can actually affect your mood as well.
Yes, so there's this whole thing about the microbiome, and it's brand new. I mean, I think watch this space. It's not my area of expertise, but what we eat will affect our health, mind and body.
And when Hannah was describing the brain earlier, she basically made it sound like a machine. Would you both agree with that? Do you think of the brain as a machine? Brett?
The computational metaphor is really seductive for thinking about the brain, that we can think of how it takes inputs and then pushes outputs that create our behaviors, and that is helpful, but it can also be really reductive to think of the brain only as a computer, and it glosses over the plasticity and the nuances of how the brain actually works.
Okay, so let's get into some of those sort of details. Helen, I know a lot of your research focuses on children, and particularly looking at how our experiences in early life can then have a further impact on how we act and how we are as adults. To what extent do you think we get what we're giving when it comes to the brain, and to what extent do our experiences kind of shape it? I guess it's that kind of nature versus nurture question. Which one wins?
They're so intimately connected. And what I find really fascinating is we're all unique. We're all unique when we come into the world. And then the way that our environment interacts with our unique person will determine the many different trajectories that you could take. And we know, for example, that people who are risk takers, if they have a very negative environment, then the kinds of risks they take might be drug taking or prostitution. But that exactly same biological being coming into the world in a nurturing environment might become a TV presenter.
I mean, it would make sense, wouldn't it? I mean, if you've had a not very good upbringing, then you would try and seek some kind of reward elsewhere. And an easy way to seek reward, some might say, is to hijack the dopamine system in your nucleus accumbens and kind of go and get some drugs.
Well, I think we
I'm not advocating that by any stretch of the imagination, by the way.
That's right. Don't try this at home.
Don't try this at home.
No, I think we are all wired to seek reward. And I think if you can get the reward from your family and your friends, from humour, from laughing together, then why would you need drugs? But if you don't have that, maybe you do.
And so you're interested in plasticity, how the brain can change to different environments. And so there must be a flip side to this as well. So we can study this and try and find out how we can make our brains more plastic in order to kind of help people to flourish.
Well, for me, it's not just individual brains, it's how our brains interact with the brains of people around us. You know, how we interact with our friends, how we interact with our families. And that is what allows us to flourish. And so I think plasticity is not just about neurons connecting. It's about how we allow our brains to practice. And we do that through relationships more than anything else.
So I'm really interested in how our brains react to our environment and different environments that we might be exposed to. And I've got a neat little illusion that I hope helps to explain how quickly our brains can dynamically react to our environments and experiences that we're exposed to. So if you can all have a listen to this. First audio file, please. So that sentence doesn't make a huge amount of sense,
Brit
right?
was looking very confused there. Did you get that?
Ideas of what it might be, but they're also
Did you get any words?
The owl is close to the cage in the zoo.
Yeah, it's got more than one. I mean, it's pretty much gobbledygook.
Okay.
Okay, so if we now listen to this second sentence.
The camel was kept in a cage at the zoo. The camel was kept in a cage at the zoo.
Poor camel.
The camel was
Not
kept
an
in a
owl,
cage
but it's
at
camel,
the
quite
zoo.
close to it. And now if we go back, we revisit that first sentence, and I promise you this is the original audio file. And suddenly, it makes complete and utter sense. So your brain has, in an instance, used that prior experience of making that there's a similar sentence about the camel being kept in the cage at the zoo, that similar cadence, and overlaid that sense onto the gobbledygook in order to try and make sense of it. And your brain is doing this all the time. It's kind of basically a prediction machine. It's trying to make assumptions of its sense of reality, its perception of the world, based on all of the prior experiences. And if you imagine that your brain is basically the output of a culmination of the unique experiences that you've been exposed to in your life, and that affects your perception of the world, your sense of reality today, it's quite an incredible concept.
Yeah, I'm really into this because talking about, kind of learning and how our brain changes, I've always kind of thought that I'm really rubbish at learning languages, right? And I've always just said, this is just how my brain is. But Helen, doing that experiment and seeing that, is that true? Am I stuck this way? Or can I change my brain? Can I train myself to be better at learning a new language?
Yes, and I know this because I did East Kilbride High School French, and I learned to say Jean Paul et Jean Le Jardin. And then I went to a lab in France. I couldn't speak for 3 weeks. They all thought I was a quiet person. And slowly I began to learn. So it's amazing what our brain can learn, and you've just got to, it's kind of use it or lose it thing. You've just got to put yourself in the position. However, my husband has been trying to sing for his entire life and has not learned. So maybe there's a limit.
So these are kind of mundane-ish, everyday examples, but Britt, you've been gazing to the future and looking at some of the extreme ways we might change or even enhance our brains using technology one day. Can you tell us a little bit more about what you've been finding out?
Sure. On the Tomorrow's World podcast, in the first 2 episodes, we explore the latest venture from serial entrepreneur Elon Musk, who created a company called Neuralink. And the idea here is to create brain-machine interfaces that allow for seamless communication with computers from right inside our brains, to allow us to do things such as upload thoughts to the cloud, connect to a type of internet, meet each other in such a way that if I were hanging out in Glasgow and a good friend of mine were in Honduras taking a hike, I would be able to tap into this brain net connection with them and feel the dew on their skin as they trek the mountain ridge or understand the look of the horizon on the sunset. Now, the way to get to that kind of high throughput approach of sharing ideas requires bandwidth. That requires a lot of implants going into the brain. And they're trying to create flexible materials that would be able to go in 1 million plus in terms of how many electrodes would fit into our brain to allow us to connect this way. But the reason is actually quite startling as to why Elon Musk thinks that we should do this, and it's because he's extremely concerned about artificial intelligence. The idea that now we are building structures that could come to be far more intelligent than us, and that is alarming in terms of there being a rogue actor or it just getting out of control. So if we can actually put artificial intelligence in our minds, and there's not just one person with a lot of power, there's no monopoly, but we can balance and check each other because we all essentially become artificial intelligence with our human intelligence in the same brain, then that will safeguard against unintended consequences of the rise of artificial intelligence.
Wow, there's quite a lot to unpick there, isn't there? I think.
I've got to admit, that sounds a little bit like someone's been watching too many science fiction movies, but it's a genuine kind of concern, I guess, yeah.
It's a genuine concern with now corporate interest funding going towards it in order to develop the tech. But looking at where brain-machine interfaces are today, we understand that that is still a very far way away in terms of getting that kind of high-fidelity machinery to create that.
Interpret from the electrical activity, to interpret the dew on the mountain. I can't remember your beautiful description there, but like, to kind of interpret those electric signals and make that vision a
That's an enormous mystery still. We don't know how to describe and characterize and locate complex thought patterns that arise from the neuronal interactions that we can interrogate. So there's this kind of middle layer of brain activity between the neurons that we know how to look at and study, and then the behavioral outputs that we understand. And that is what needs to be solved before we could do something such as isolate language and then just teach you how to speak Mandarin by sending that package of information to you through the brain net.
But there has been some incredible progress in the last 5-10 years, for example. So there's cyborgs that are living amongst us at the moment. So, for example, people that have hacked their brains so that they can now hear in colours. They've got a form of synesthesia, so they've changed the way that their brain works so that they can now hear. Or you can now get cochlear implants so that people can hear when before they were deaf. So there has been progress made in little steps going towards this vision.
Absolutely.
And are there any other kind of really cool examples of brain-machine interfaces?
There certainly are. Imagine you suffered a stroke or a brainstem injury and you're paralyzed. But now, with the power of thought alone, you can control a robot arm, a prosthetic appendage to be able to feed yourself, fist bump a friend. This already exists. So I went for the podcast to Andrew Jackson's laboratory at University of Newcastle, where they have a variety of machines that they're developing, microelectronics that fit into the brain and can record our neuronal activity. So these microelectroarrays are about 4 millimeters by 4 millimeters, and they look like a bed of nails or a really uncomfortable small Barbie hairbrush with about 96 pegs that come out of them. And you can go under the scalp, put them on the brain, as well as insert them on the arm-shoulder area and the wrist-hand area, and listen to neuronal activity, about 200 to 500 neurons at a time. And if you can do that in real time, which they can, and you understand the directional preference of these neurons, because it turns out that neurons all have a way that they want to move. So in something which is essentially like an election where they're each voting for which way they want to move, you can count that up and then understand this cluster wants to do this. Okay, well then we can take that information and send it to a computational device which is hooked up to a prosthetic arm. And therefore, when that person is urging to reach a piece of fruit, that electrical stimuli will go to the arm and then get the piece of fruit for them. And this is happening.
So I think my reaction to everything in this show is going to be that is seriously cool, but it's also slightly freaking me out. You can hear more about the future of brain-machine interfaces on the Tomorrow's World podcast hosted by Brit along with Ellie Cosgrove.
But moving quickly on to a question that's come in via Facebook from audience listener Tom Paul. I think this is a question for you, Helen. He's asking, do kids and adults fully understand how life choices or habits impact in the long term on the brain? Do doctors even know this?
That is such an interesting question, and I'm not sure the answer to that. I mean, we know that if you want to change a habit or form a new habit, it's going to take about 3 weeks. So you really have to work at it. So I guess that's a really good example of brain training. Mm-hmm. So I think psychologists...
Could it be changing the connections in the brain?
I think it could.
So forming something that's learnt becomes a memory that becomes a habit because you keep on revisiting that pathway of electrical activity in the brain, and then it becomes like almost the motorway in the mind, you know, the default route by which you get to London or whatever.
Absolutely.
Or Glasgow.
I think a good example is typing or playing the piano. Mm-hmm. Typing is probably an example that we can all think about. We know, for example, that if a secretary wants to increase his or her typing speed, he or she's going to have to kind of stop and start again because you've got muscle memory. So you've got really good at it, and then you have to get bad at it again and learn anew, if that makes sense. You have to learn to do it a different way. And I suspect what's happening there is you're actually retraining your brain, and you're using different, you know, you're kind of emphasising different pathways.
And as there's been studies that have amazingly imaged brains as people learn a new skill or a new habit of behaviour, and you can actually see certain areas of the brain bulk up in terms of their connectivity, and also the axons and the dendritic connections within the nerve cells there, as they keep on revisiting and replaying that memory and kind of keep on exercising that habit. It's fantastic.
I think that's what's so exciting about the brain, because, you know, when the heart, for example, when you're born is like a little heart, you know, the shape of it's not really going to change, but the brain can really morph and change over life, which is and right until we die.
That's fantastic. Well, if you've just joined us, this is Tomorrow's World Live from Glasgow Science Centre, and we're talking about how new technologies are allowing us to explore the very inner reaches of the human mind. There'll be more opportunity for questions to be asked later, but next we're going to introduce our next two guests.
So with us are Glasgow University psychiatrist Helen Minnis and Tomorrow's World podcaster and science communicator Brit Ray.
Do keep any of your questions coming on Facebook. You can leave questions on the comment section of Facebook and also YouTube. And you can get in touch on Twitter using the hashtag #MyTomorrow.
Now, if the human brain is science's final frontier, then our next two guests are voyagers, boldly going where few of us have gone before.
Beautiful.
I can't believe they made a Star Wars nerd make a Star Trek reference.
Bit mean.
Bit mean. Please welcome, from Cambridge University, Royal Society Dorothy Hodgkin Fellow, Dr. Anna Laura Van Harmelen.
And currently based at Oxford University, but now back on his home turf for one night only, Dr. Martin O'Neill. Big round of applause, please.
Martin, we've just been talking about how it feels like we're on the cusp of exciting discoveries and extraordinary discoveries. You both work in brain science. Does this feel like an exciting time for you, Martin?
Yes, absolutely. Yeah. Exciting time now. I've been engaged in this research for 15 years, and it actually just increases at a phenomenal rate, actually, the excitement, mostly due to advances in technology, which are accelerating all the time, which is fantastic because of the amount of data that these advances in technology produce. But it's also challenging as well, because we need to be able to make sense of this data. But I think we are up for the challenge.
Absolutely. And so the brain is so incredibly complex, and there's so many different facets of behaviour that we need to try and unpick. Which particular areas of brain research are you guys interested in? Anna-Laura?
So I study the effects of child abuse and neglect on later life, and in doing so I want to understand why some children go on to develop mental health problems, whereas others don't. So that is really studying both risk and resilient functioning after really negative experiences.
And what kind of impact will that have? I mean, can you actually kind of determine whether someone's going to have resilience and kind of flourish later on in life?
Well, that's really important, is to know what resilience actually means, because it's such a buzzword that people really like to throw out, but they don't really, often don't really think about what it actually means. And what we think it means is that it's positive adaptation across relevant domains of functioning after early life stress or after a stressor. So basically bouncing back in terms of your mental health. And so you can only study it in terms of functioning. You can't really measure resilience itself, because that is something that it's a process of adaptation. But what we're actually measuring is how well someone is functioning. So we can measure if you've had early life experiences, and we can also measure how well you're doing in terms of your mental health. So we can know or infer that you're resilient or not.
Okay, so I think we've got a question from an audience member in the room with us, David Kirk. We can get a microphone to you if you want to ask your question.
How do I decide in my mind what is good or bad decisions?
Martin, do you want to take that one on?
Yeah, thank you, Uncle David. Yeah, that's a great question. How do you decide in your mind between a good, well, probably based on the outcomes of your decisions. So you make a decision, you then you have your effect on the world through your action, and then you evaluate the outcome of your decision. Okay, so either the outcome will either be rewarding or positive, or negative, a punisher we would call that, and then you would update based on the outcome from your decision. That's a sort of...
And this is your particular focus of research?
Yeah, so decision making is my area of interest. And decision making, but also the biological basis of decision making. So the electrical signals that Hannah was describing earlier on. So I record those signals from neurons from within the brain to try and characterize how these signals are involved in decision making processes.
So Martin, you've kind of started talking about this, but at the beginning of the show we were talking about new technologies in brain research. And so what are the new technologies that you're using in your work?
Okay, so when I started this research, we were using single electrodes, recording from single neurons, one at a time. Now we can implant electrode arrays, which are about a quarter the size of my pinky nail, with 100 electrodes on an implant that size. And we can implant them in multiple brain regions as well. And also that the advances in technology mean that we can record that amount of data, because that is a vast quantity of data to be recording from that many electrodes in the brain. So that's been really a massive step in terms of the recording side of things. The second part of my research, which relates to, I think, what Brett was talking about earlier on about brain-machine interfaces, is actually making sense of this information, okay? So we can measure all these electrical impulses, but we need to be able to make sense of this information. And to do that, what we use are these decoding techniques. So if we think about a brain-machine interface, you take the electrical signals from the brain, then you need to understand, you need to feed those signals to a machine. And that could be a prosthetic device or a robot. So you need to be able to decode that for it to have meaning. So that's a big challenge, and that's something that we're actively working on at the moment, and that's really a fusion of fields as well. So this brings computer science, robotics, machine learning. So I'm just trying to figure all that stuff out at the moment.
And we should be clear that much of the research around these new technologies is being conducted on animals. Is that necessary? Are animal brains similar enough to our human brains for this to be useful?
So, yeah, I guess the answer to your question is in your question. I think the animal research is necessary. It's highly and strictly regulated in the UK by law. So animal research can only be carried out with a license granted by the Home Office, by the government, to institutions and individuals. And in order for those licenses to be granted, you need to justify that there are no alternative approaches that can be used. So, and these licenses are also regularly and frequently reviewed and monitored to ensure those really high standards are maintained.
Thank you, Martin. Yeah. And you're working on very small numbers of neurons, and yet our brain contains billions of nerve cells with trillions of connections between them. So the main problem facing brain science is that one single lab or one single person can't study all of that by themselves. So even an apparently simple task, for example, how do we decide if it's safe to cross the road, that might take decades for scientists to map all the neuronal activity involved. But perhaps we could find out more if labs across the world came together to start to analyse this question in a multidisciplinary approach. Earlier on, we recorded this interview with Alexandre Pouget. He's the spokesperson for a really exciting project called the International Brain Laboratory. It's only 3 months old, so it's a little baby project, but there's huge ambition behind it.
The International Brain Lab, or IBL for short, is a consortium of 21 laboratories spread across the world whose collective goal is to uncover the neural basis of decision-making and foraging. Currently in neuroscience, most labs work in isolation and therefore compete for resources and results. Given the complexity of the questions that we're now facing in neuroscience, this model is no longer sufficient. This is very much like the situation faced by physicists. While Newton was able to uncover the laws of gravity on his own, it took an army of scientists at the CERN to discover the Higgs bosons. In IBL, every lab will record from a specific area of the brain, while the animal is performing the exact same task. This way, we'll be able to combine the data we collect into the first brain-wide theory of how the brain makes decisions. Now, why perform this experiment now? Well, simply because we're at a watershed moment in the history of neuroscience. We finally have the tool that allows us to see the activity of extremely large population of neurons, while having the technology that allows us to collaborate efficiently across continents. Ultimately, we're interested in more complex behavior, such as how we decide our career or how we make financial decisions, but this, of course, will be the topic of future work.
That was Alexandre Pouget speaking to us from Australia yesterday.
And this is really cool because it kind of sounds like it's the CERN of neuroscience, right? Scientists from around the world coming together to work on some of the big questions.
Very exciting, very multidisciplinary approach where everyone's kind of attacking the questions about the brain from different angles.
Yeah, great. Let's have another question from our audience. And we've got another question from someone who's in the room with us. Harry Brannan from here in Glasgow wants to know, being autistic, how will autism be treated in the future? Who wants to tackle that? Anyone?
I'd love to say something about that. I think our thinking about autism has just exploded over the last 10 years or so. And there's a world of very successful people with autism who are showing us it's just a different way of thinking. So I've heard it said, and I really believe it to be true, that we would not have invented the wheel had it not been for people with autism. So autism can... The way people think when they have autism is they'll see a lot more detail than someone without autism, and obviously that can be an advantage, but it can also be a disadvantage if you've got additional detail coming towards you that's distracting you from something that you're trying to focus on, or that's distracting you from the whole. So autism by itself is not a disorder. It's only a disorder if it actually is causing problems for the individual.
And this kind of comes into a question that we've been talking about quite a bit in the prep for this show, which is there such a thing as a normal brain? What do we all think? Anyone? Martin, you look like you want to speak up.
Yeah, it's a tough question. My answer is no. Otherwise, we wouldn't all be different. So our brains have to vary in order for us to be individuals, but also this idea as well of autism. I think maybe perhaps in the field of psychiatry, we're sort of trying to move away from categorization as well, because a lot of people have a whole mixture of traits, that can be expressed to different degrees in different people, and sometimes these do end up causing problems. So in that sense, no, and also if I can put my sort of neuroscience hat back on. I think you mentioned like 100 billion neurons in the brain with thousands of connections between them. I mean, it's just not possible for that model to be consistent across individuals. There's so much variability in there, which we can think of as personality and individuality, but obviously that's going to result in very many different personality traits and across different spectrums as well.
I have a colleague, Chris Gilberg, who's probably done more research on autism and ADHD than anyone in the world. And in his lab in Sweden, he's got a poster that says, "Normal is way overrated."
We've had another great question in from an audience member on Facebook. So apologies if I pronounce this wrong. Kashita Yadav, what do you think soul is? Is it in the brain? Pretty deep, reaching question there.
Britt?
I definitely think the soul is in the brain. It might be beyond the brain. Chicken or egg, do you need the soul first to have your brain and mind function the way that it does, or the inverse of that? I'm not sure, but I do feel that this is an exciting question that we will never, ever get to the bottom of, and that philosophers have at least as much as neuroscientists to weigh in on.
Anna-Laura, would you agree with that?
Well, no, not necessarily. I do think that the brain and the mind are the same thing, and I'm a bit sad by that, really, because
You do think they're the same thing?
I do think they are the same thing, so I'm a bit more deterministic in that sense. And I think the brain is such an interesting, complex thing in itself that is really beautiful, and there doesn't really need to be more than that.
Are you equating the soul with the mind then?
Yeah, that's a good question. I might be.
Then the brain would be the soul, according to that equation.
Yeah.
Cool.
But the brain also interacts and is regulated by other areas of the body as well, as we were discussing earlier. But in essence, that is us. Yeah.
Yeah.
Well, we're getting pretty deep, so I think we should maybe move on. You're watching Tomorrow's World Live, where we're putting your questions, your deep questions, about the brain and everything related to it, how we might treat it in the future. We're putting all of your questions to our panel of top experts. Please do keep them coming in on Facebook, YouTube, and Twitter.
We're live here at the Glasgow Science Centre, part of Tomorrow's World season, which is brought to you by the BBC in partnership with fantastic institutions like Wellcome, Open University and the Royal Society.
And you can keep up with new science stories from our partners on the Tomorrow's World website. There are videos on mental health, from the issues facing new parents to body image.
There's also more about the future of the brain in the Tomorrow's World podcast, available now from your favourite podcast provider and presented by Ellie Cosgrove and Britt Ray. Britt, tell us in 20 seconds, absolute maximum, what's the most fascinating thing that you learned during the podcast research?
I've been absolutely floored by learning that there are a variety of technologists, philosophers, scientists out there who do think that it's plausible that everything that we wake up to every day, everything that we've known since we were born and entered the world, is simply potentially a product of a far more civilized group of life forms that are running simulations, and that we are cogs in the simulation.
Sorry,
and that
who says this?
Nick Bostrom, philosopher and researcher at the University of Oxford, Future of Humanity Institute, has a premise by which logically you can't shut it out as a potential of what makes the world tick.
Wow. Okay, so...
That was my reaction.
Did he give a probability for that? Like, what's the probability of it? No?
Trying to describe that in mathematical terms, I was too confused. I'm not sure.
I like how we went from the deep subject to something a lot lighter.
Well, we've talked about how imaging and other technologies are giving us a more detailed picture of the brain than ever before. We've talked about how we might enhance and treat the brain and change processes like decision making. But all of this raises big questions. Martin, is there a risk to changing the way we make decisions? Are we opening up new types of mind control? Does it need regulation? Please tell me it needs regulation.
Well, yeah, I think that term mind control is kind of unnecessarily, no, it's provocative, but it doesn't need to be negative. I mean, I think we've sort of got these, you know, we all think Terminator in terms of robotics and mind control is, you know, these sort of supervillains are going to hijack our minds, and that's not the way the scientists approach it. So the way that I, no? Yeah.
But can I just say that if we understand more about the nuances of how we make decisions, then that does increase the scope for us to possibly manipulate, or not us, but some people to manipulate how we make decisions, right?
Yeah. So I think the issue that doesn't concern me in the research field, but I think the point was raised earlier. If industry starts to take over the sort of technologies that can develop from these approaches, then that may be a concern.
But as a researcher whose day job is kind of studying the nitty-gritty of our decision-making, you also presumably have to think about the wider implications of your research, where it might lead.
I do, but I'm optimistic on that front. I take a more sort of benevolent. I see that as we're going to use that for good. So for example, the approach in my research, so I record this data, we try and decode this data. The next stage, and this is to come, we're not doing this just yet, is then feeding this, if we can produce this sort of electrical model, of a cognitive process, if we could then feed that back into the brain and stimulate the brain, can we therefore create a memory, for example? Now, I appreciate how far out there that sounds, and it might sound a bit ominous, but for us, that's a test of, we actually can, we've understood the signal, we put it back in, and we can create this outcome. Now, from a benevolent approach, or a positive, optimistic approach, I would like to think that can be applied in mental health conditions where decision-making breaks down, okay?
So somebody who's depressed, for example, could have implanted a positive memory or a new habit, a new way of looking at the world in a more positive light.
Yes, and in obsessive compulsive order as well, where people sort of, they react to stimuli in irregular ways. And that's, this sort of approach has been used in Parkinson's disease, for example, so deep brain stimulation, which is remarkable. I mean, if you look at any of this footage of people who have really severe Parkinson's disease and have electrodes implanted in their brain.
So their skull is kind of surgically opened up, and then an electric shock panel is effectively kind of buried deep in the region of the brain that's involved in
Parkinson's. Opened up, electrodes implanted, everything's closed up, and even the battery pack for the electrodes is implanted below their chest muscle, and they can control it with a remote control. And this footage is amazing. So if they turn the power pack, the battery pack off, their Parkinson's, they can't move. And they just turn it on, the electrical stimulation, they can move again. Now, that's very coarse. That's just a bunch of electrodes sending quite a wide, strong signal in there. But with my work, using all these, hundreds of electrodes, trying to decode these signals, it's possible that we could perhaps help people with more nuanced deficits, like an obsessive-compulsive disorder, for example, possibly. That's how I view it.
Yeah, and this deep brain stimulation has also been kind of trialled for heroin addiction, treating that, for example, and other mental health kind of conditions. But there's lots of ethical considerations associated with this research. Anna-Laura, you're interested in something that we kind of touched on in our previous show about robotics and artificial intelligence, and that's using clever smartphone technology to try and decipher which individuals, which young people might be at risk of mental health kind of conditions later on in life?
Yeah, so this is this is research that we'd really like to do, but so we're planning to do this, but we haven't got the funding yet. But this is a really exciting new thing that I really want to do, is that it's to study adolescent suicide behaviors, and the reason for that is that adolescent suicide is the second leading cause of death in adolescence, and we don't know who will go on to commit suicide. But we do know that 16% of adolescents think about committing suicide, and that a third of them actually make an attempt. But we don't know what the risk factors are. And over the past 60 years, our knowledge hasn't improved. So what we want to do is we want to use cell phones or smartphones to better study adolescents who are at risk for suicide behaviors and suicide, might go on to attempt suicide. And by continuously following them over a period of time and assessing what they say online and what music they listen to and what kind of pictures they take and what their movement is, their sleeping patterns, basically everything they do, and to upload that to the cloud and to have a machine analyze that, because we have the new technology that is able to actually really disentangle this complex amount of information automatically. So it's all anonymous, but we have the new technology that's better able to examine this and to hopefully provide us with new risk factors.
So you're taking a two-pronged approach, really. So you're looking at the biological factors for resilience to help protect the brain and behaviour, but also the behavioural outputs that might predict whether someone's at risk of mental health. What are the ethical implications for this kind of data being available?
Yeah, there's got to be some risks to this, right?
Well, that's really interesting. So there, of course, are ethical issues. Like we need to make sure that it's very clear that all the data that we would be collecting is all stored using really high encryption. We have double encryption software, and that no one will actually go and see the pictures that we are being taking. It's all being analyzed by computers, by machines, but what happens if an adolescent would write in a text, "I am going to commit suicide today"? That is an important thing that we then would be able to actually, in that moment, we would be able to automatically send a text to the person saying, we have detected that you might be at risk, and here are the numbers for you to ring if in case you want to have some help, in case you want. And we would also receive an automatic text where a clinician could ring the person. So actually, in studying adolescents, there's always this risk of suicide behaviors. And this study will be the first that would actually be able to intervene in time for these adolescents.
I think there's kind of a lot of discussion that we could have around that, about technology and smartphones and how much our phones know about us. I get a little bit freaked out by my smartphone knowing where I live. But we've got a little bit more time for some questions from the audience. So here's one that I want an answer to, which has come in from Zoomer1979 on YouTube. Does anyone see a time where anything you need to know or learn can just be downloaded to your brain? Britt, what do you reckon?
We have a lot of describing to do before we can get there. We need to understand how large connections of neurons actually produce these outputs, these behaviors, these traits that we might want to establish in our brain without going through the tough work of going to night school and learning that language or whatever it might be. So that really is a huge issue that I heard stated again and again by all the neuroscience experts that we interviewed about the future of being able to bypass basically a lot of time in order to train ourselves to do certain things and simply get a download of information. And then there's also the question of brain uploading, which is something that people talk about. How can we potentially achieve our own digital form of immortality by uploading our brain to some kind of server that would keep it after our bodies perish? But there's a huge problem here, which is that when you interrogate a brain, when you measure a single neuron in order to get the structural scope of what you want to upload, you change it. This is this issue in terms of being able to describe the holistic package of all of the neurons, is that when you go in and when you touch and measure, you actually then make an effective change, which means that you're no longer uploading what you originally set out to. And so this plasticity and this difference makes that a really big challenge.
But in a sense, do we not already have that? So, you know, the books of Oliver Sacks, you know, he's dead, but we have his books. So, you know, it's the outputs of our brain, in some ways, that's an upload, isn't it?
Well, absolutely. And do we even need to go to the level of neurons in order to immortalize an essence of someone? What if we just did a battery of tests on you to see how you react in certain conditions and how you make decisions, and then store that information to be able to emulate it at another point?
The question is also, when do you store the information? Because memories change over time and experiences change over time. So when do you upload your brain? When you're an adolescent or when you're an adult? When would we do this?
Okay, folks, I hate to interrupt this, but we've got time just for one more question from Rachel Spires from Invacip, who I think is in the room, and we can get a microphone to you. Yep, do you want to ask your question?
So, in the near future, what areas do you see holding the greatest potential for breakthroughs within neuroscience?
Okay, so we can expand that to the greatest potential for breakthroughs in neuroscience or just brain science kind of in general. Anna-Laura, do you want to tackle that first?
Well, yeah, I think obviously smartphone technology, using that to study mental health disorder and to study risk in mental health, that will be a really highly potential for great breakthroughs.
Okay, great. Martin, super quickly.
Okay, yeah, I think the tools are becoming a lot more advanced in terms of the specificity with which we can actually achieve mind control in a positive way. So like optogenetics, for example, is the kind of sexy technique in neuroscience at the moment, where you can actually control animal models, neurons with different colors of light by light-sensitive molecules, which can be engineered on these neurons. So we're able to achieve a much greater degree of specificity now in terms of nice mind control than we could before. Yeah.
And Britt, greatest breakthrough for you?
I think watching this space as it becomes more finesse to create rehabilitative technologies to regain function, motor control, and even sensation for people who have not been able to feel their bodies in a very long time will be something that we see a lot from.
Helen, final word on greatest potential for breakthroughs.
For me, I want to know how brains interact with other brains. I'm not particularly interested in single brains. I want to see how they work together.
Nice. That's a really nice way to finish. Thank you all so much for sending in your questions about the brain. Sorry we didn't get to answer all of them, but unfortunately that's all we've got time for here on Tomorrow's World Live.
We've had a fantastic time this evening exploring the latest technologies that shed light on how the brain works, what happens when it sometimes becomes ill, and what we can do to help enhance it in the future.
Although I'm still not quite sure whether I'm more terrified or excited about the idea of a mind-machine meld.
I think you're very optimistic. I mean, my brain is sparking with electrical activity of excitement, I have to say, by all of this.
I think I'm still slightly freaked out, everyone. If you joined us partway through the show, you can find the full video online. Just search for BBC Tomorrow's World Mind Control. You'll also be able to find it on BBC iPlayer in a few days' time.
You can also watch our previous episodes on space travel and robotics. Just go to the Tomorrow's World Live Facebook or BBC YouTube channel.
Thank you to all of our panellists, Helen Minnis, Britt Ray, Martin O'Neill and Anna-Laura Van Harmelen.
And also to our contributors, Yolanda Ahini and Alexandra Pouget.
And also to our presenters.
Yes. Thank you. Did I forget anyone there? No, there's Jen. And if you want to carry on the conversation about anything that we've talked about today, then go to the Tomorrow's World Facebook page or use the hashtag MyTomorrow on social media.
But that's it for tonight. Thank you so much for joining us, and from everyone here at the Glasgow Science Centre, goodbye.
Goodbye.